Welcome back, ladies and gentlemen. So, last time we started off with learning how the sentences of chemistry work, how the balanced chemical equations work. We saw a variety of chemical equations, right, where we took sentences that describe what is happening with reactants and products, and we talked about how we could put those together, but there was a critical thing. Everything that goes in must come out. So we had to make sure that all of the atoms that we have on the reactant side are balanced by all the atoms on the product side. So here are some examples of ones that we would have seen, right? Mg plus O2, and of course oxygen is O2 because it's one of the diatomics, those guys in the top upper corner, right? I have no bright or clever friends. Those guys will make double diatomic atoms, they'll double up whenever they're alone. When alone is the key. In this particular case, right, we have to be able to make sure this works. Magnesium is in the second family, which means that magnesium has a charge of 2 plus. Oxygen has a charge normally of 2 minus. I mean, once it becomes an ion, which it will in this context. So we need to make sure that these all work. Well, 2 and 2 means I'm going to get MgO, which is what I've written here. So okay, so far so good. We can erase those charges because we don't need them anymore. Now what we need to do is make sure that the chemical equation is balanced. Now, of course, we can do that by writing out a chemical inventory, listing everything. There's magnesium, there's oxygen, there's one over here, one over here, one over here, and 2 over there. So there's the one that's going to throw us off. So, as we discussed last video, we're going to multiply by 2 in order to make them the same. That means I got to put 2 in front, which means this one's times 2. Which, of course, messes that one up, but it's okay. That's okay, because what we see is I just have to put a times 2 here, and I'll be good. So I throw a 2 in front there, and I'm done. That's it. I know, I went through that pretty quick, but I'm hoping at this point you guys have gotten lots of practice on this type of stuff. So we'll erase that just to make it cleaner. So there we go. We've got a balanced chemical equation. Now, what about the next one? Something's wrong with it. Did you catch it? Charge on fluorine is, of course, 1 minus because it's part of the halogens. Charge on calcium, because it's in the alkaline earth, is 2 plus. This doesn't work. This is missing something. It needs to be CaF2. And of course, the key for this was that everything that goes in has to equal everything that comes out. So if I look at that closely, I'll see I've got 1 calcium here, I've got 1 calcium here. I've got 2 fluorines here, I've got 2 fluorines here. We're done. It works as is. We don't need to do anything further. I mean, again, we could erase the charges just to clean it up. And there we go. So this is what we did last time. This is how we put things together. This is how we learned about how these sentences behave. But there are patterns. And as we've discussed before, if you know the patterns, it makes your life easier because you can take a bunch of shortcuts. Can you spot the pattern with these two? Obviously, it's not the elements. The elements are drastically different, right? We've got magnesiums and oxygens, calciums and fluorines, no similarities. It's not even the way I wrote the structure. This was just 1 and 1. This is 1 and 2, so that's different. It's not even the balancing, right? This didn't need any balancing. This one, I did need to do some. No, the pattern is if you look at the reactants and the products. I have 1 product in both of these. I have 2 reactants in both of these. If you think back to the practice that you hopefully did, you'll remember that there were lots of instances of this, of similar number of pieces being put together, if not different pieces themselves. 2 reactants, 1 product. You may have also seen situations where there was 1 product or 1 reactant and 2 products. What we're seeing here is that there are types of reactions. The purpose of types of reactions is that it simplifies a lot of our work because there are literally thousands, millions of different chemical equations, different chemical structures that we can make. Trying to memorize all of them would be worse than trying to memorize the entire periodic table, and we already don't want to do that. So instead, we group them into categories. Now remember, the purpose of categories is to make it easier to understand something. In the case of the periodic table, we grouped the elements into families, right? The vertical columns. And each family has certain traits or attributes that are in common. Well, in the same way, we can take a bunch of different chemical equations and group them into families or categories, similar features that propagate through all of them. There are about 6 chemical reactions that you're going to see over the course of grade 10. We're going to take a look at 5 right now, and the 6th one will be at the end of the entire unit. It's special, what can we say? Right now, we're going to start with this one that we've got on the board. This has a particular name. We call these kind of reactions synthesis reactions. A synthesis reaction looks something like these two, right? It's basically where you take two relatively simple things and you make one complicated product. Synthesis is sort of a fancy way to say combine or bring together. So we're bringing things together. We're generally going to get this combination of simple to complex. I almost wrote complex. All of these chemicals, or all of these chemical equations of this family have a particular way to write it. It's basically A plus B makes A B. You expected me to put C, didn't you? Yeah. This is sort of considered a general way to write an equation. Right? We're using letters. So those of us who are pretty comfortable with algebra are going, yeah, and those of us who hate algebra are going, no. What I'm saying is, of course, is that we've got two fragments, two pieces that then combine together to make the total. So this is our first option. This is a synthesis. There's a binary choice here. I take two simple things and put them together. Okay, fair. What happens if I take something big and break it into two pieces? That's the next one. We call that decomposition. Decomposition is, again, the fancy way to say decays or falls apart or breaks down into smaller and smaller pieces. An example of a decomposition reaction could be something like HgO goes to make Hg plus O2. Remember, the oxygen, diatomic, will be paired up if it's alone, but when it's with the mercury, it doesn't pair up. Well, it's not balanced. This one should be pretty quick, though. Like, we don't even really need to do a full elemental inventory. We can just sort of look at this and go, that's a 2. Put a 2 there, and a 2 here. If you've done enough practice, you're going to start finding that you can do that, where you can just look at it and be like, I got to make the two sides equal, so let's just do this. Let's go. So what we see with these guys is that we tend to get complex breaking into simple. And in terms of the generic form, it's going to be something like AB goes to make A plus B. It's the opposite of the synthesis reaction, right? So synthesis puts things together. Decomposition takes them apart. And we can see, if I get out of the way here, that they both have the same result. It's just located in different places, right? These two become this. This becomes these two. Okay, that's our first two types of reactions. Pretty straightforward, I hope. But there are more. Not all of them are this easy, but they are connected in some ways. We're going to need some space, though. So our next one is going to be called a single displacement. A single displacement. Well, remember, as we've discussed many, many times, chemists are bad at naming things. Legendarily bad, which means that this is probably named exactly what it is, but they changed the language. It doesn't even seem like they changed the language this time. It's just single displacement. So what does a single displacement reaction look like? Well, it's exactly what it says on the label. You've got something like, say, zinc plus some good old hydrochloric acid. Normally I would get you guys to do this experiment in the lab, and then we would be able to talk about it. And when you do that, you're going to get zinc chloride plus H2. Now, if it's balanced, we have to check, right? We'd have to see what's the charge on zinc. We get down our periodic table, and we take a look, because if it's ZnCl, we're good. But if it's not, then we're not. So we pull out our periodic table, we take a look here on our second page, and we find zinc. And zinc is right there, and it says that it's 2+. So we're not good. It's not ZnCl because the Zn is Zn2+, and the Cl is 1-. So if this one is 1 and this one is 2, that means that I need to change my chlorine, like so. All right, get the charges out of there. We've done the first step, which is to balance the left and the right of the ionic compound. Now we have to balance the left and the right of the whole sentence, the whole chemical equation. All right. Well, actually, this one's pretty easy. I got a 2 here. I put a 2 there, and I'm done. Sometimes they're not hard. What can I say? So what's the whole thing about a single displacement? What's going on here? Well, it's not as simple as complex and simple. It's about movement. And what we can see here is that the zinc and the hydrogen switch places. Originally, the zinc was alone, and the hydrogen was combined. But at the end here, we've got a zinc combined and the hydrogen alone. So what we discover is that a single displacement is like the hydrogen and the chlorine here. They were dancing together. Then zinc shows up and is like, excuse me, could I step in? And hydrogen said, why, of course. Hydrogen bowed out, went, maybe got a drink at the bar or something, and the zinc and the chlorine head off to the dance floor together. The only problem with this analogy is that there's 2 chlorines, but don't overthink it. Don't overthink it. Now, in terms of what this looks like, again with the generic form, we've got A by itself plus BC goes to make, now this we always have to make sure we're careful, it's AC plus B. So this case here, the A and the B flipped places. Now, why did A and B flip places? Why didn't A and C flip places? Because we have to remember, the rules for ionic bonding still hold. Zinc is a metal. Chlorine is definitely not a metal. So the zinc is replacing the most metallic of the 2 options, right? Of these 2 options, hydrogen is more metallic than chlorine. So the zinc is going to swap with the other metal partner. All right, so this is single displacement. Now, you'd think, okay, fine, last time it was synthesis and decomposition, and they were binary, they were opposite of each other. We're going to make something opposite here? No, I'm sorry. Not everything is simple. Now, on the plus side, what we're going to do here is not incredibly complicated. We're going to do double displacement. Ooh, so amazing. Yeah, all right, fine. Yeah, it's pretty straightforward. I mean, it's going to be more complicated because it's double displacement. You're doing twice the work. But it's going to be straightforward. Let's change up our chemical equation here. So for this one, we're going to take a look at something like iron sulfide plus good old HCl again. Didn't need to erase it. And that's going to make for me some iron chloride and some hydrogen sulfide, I guess? Yeah, hydrogen sulfide. Now, we got to check all our charges, though. We got to make sure this lines up. Sulfur, of course, is 2 minus. It's always 2 minus, which means that we know what the iron is, right? The iron has to fit. There's one of each, so the iron has to be its equal opposite. So this is iron 2 plus. So over here, if this is iron 2 plus, it hasn't changed, right? It doesn't magically transform. It's still iron 2 plus, which means this is going to be 2 plus and this is going to be 1 minus. So I need 2 chlorines to balance. Same thing over here. This is going to be 2 minus. This is going to be 1 plus. So I'm going to need 2 hydrogens in order for that to work. Just because we're doing this whole balancing stuff, just because we're doing this whole groupings of chemical equation stuff, doesn't mean we can ignore all the things we learned before. You need to know how to put words together before you can do sentences. And if you put your words together wrong, your sentences are going to look pretty funny. So, what do we see here? Well, in much the same way as before, the iron swapped places with the hydrogen because both of them are cations. Now, why do we call this a double displacement? Because instead of this guy being alone, this guy over here was already combined. Same thing over here. I don't have anything alone at the end, I just have something combined. When I scribble it out here in terms of the broad approach here, we start off with an AB, right? We have a combined thing here. We have a complicated material with multiple pieces. And we've got C and D, another complicated material with multiple pieces. But then they switch, and we saw that A and C switch places. So we're going to get CB plus AD. That's always the tricky one, right? Because it sounds so weird. It's like AD? But it was in alphabetical order on the reactant side. I know. So what are we seeing here with this? Again, it's the same as the single displacement. It's just that now, instead of, say, as we did last time, 2 of them are dancing, one of them walks up and goes, "Excuse me, could I have the next dance?" Instead, there are 2 couples dancing, and then they get close to each other, and in the middle they sort of swap dance partners. Now, again, we have to be careful. Cations replaced with cations, positives with positives, metals with metals. I just said the same thing 3 different ways. In the same vein, right here, right, we've got ourselves a marker. It's got 2 pieces, this and this. They fit together. You've got your metal and your non-metal. Well, if I have a second marker here, I can do a double displacement. I can take off the metal, and I can swap which ones fit. But you'll notice, they had to fit. They have to make sense. I can't just take these 2 pieces here and try to jam them together. They don't fit because these are both metals. They don't dance with each other. They swap to the other non-metal, like so. So that's basically what we have going on here. We start off with a fully red marker and a fully blue marker, and then through the process of chemistry, they swapped dance partners, and we ended up with 2 pieces like this. In the case of a single displacement, it would be more like we had a single dance partner like this, and there was 1 cap just floating around, and then we just swapped the caps, and there was 1 cap off by itself. So that's the difference between single displacement and double displacement. It's just whether or not the other cap has something on the back end. Otherwise, it could just be sitting there by itself. Those are by far the most complicated, and we must remember, right, this is so critical. I'm going to write it down right now. I messed up the S, and I put an extra E. Metals swap with metals. Non-metals swap with non-metals. If you mix it up and you put 2 metals together, it's like you're trying to take 2 caps and putting them together. They don't click. All right, that's number 4. We've got 1 more. And on the plus side, this one is by far the most awesome, and in some ways the most easy. We're no longer going to be displacing. We're not going to be synthesizing. We're kind of decomposing a bit. What we're going to be doing is combustion. Combustion is the fancy science way of saying we're going to burn stuff. Well, all right, to be fair, we're not going to burn stuff at the moment. We're learning the chemistry behind it. We'll do the actual fire later. So anytime you're going to burn something, it's kind of going to follow the same basic pattern. Let's do a simple one. So we're going to do, say, C2H6 plus O2 goes to make H2O plus CO2. I think that'll do for us. Now the balance for this is going to be a little bit more of a mess. So let's do a full chemical inventory, a full elemental inventory. Okay, we've got C, we've got H, we've got O. On this side over here, we've got 2. Over here, we've got 1. Here, we've got 6 and 2. Over here, we've got 2. And now the tricky part, you've probably seen a few of these, but this is the first time I've done an example on camera. 1 and 2. I separate the oxygen into the 2 different places that it is, because if I put it all together, if I just put a 3 here, I won't be able to do the math properly. It's not going to work. I need to separate them to track each of those examples of oxygen separately. Now, generally speaking, you don't want to touch the big complicated guy. You want to leave that one for the end. That's one of our rules. So we're going to go with this one times 2. So I put a 2 up front here, and that's going to times not this one, but this one times 2. So that makes 4. Okay, that's it for blue. Well, let's not put the red cap back on there. That's probably bothered a few people. We are going to pull out the red color, though. So now we've got this one figured out. Now we can do the hydrogen. So we're going to times this by 3 to make 6, because that's what I have over here. So that means a 3 in front. That's going to times 3. That equals 3. So at this point, I've got 3 and 4. So in total, I have 7 oxygen. On this side, I have 2. I don't really have a number that I can multiply by to get 7 when it's 2. Not really. Okay, that's not totally true. There is a number. What is it? It's a decimal, isn't it? Right? If I take 2 and times it by 3, I get 6. If I times it by 3.5, I'd get 7. Problem is, as we've discussed, you can't have half a molecule, so I can't put a 3.5 there. So this isn't going to work. Or is it? You see, it turns out there's a secret here, a little trick we can use. Some of you would have already seen this, but maybe not all. You see, this is a 3.5, but in order for me to fix this, I'm going to have to increase the complicated one, right? The one I said don't touch till the end. Well, that's what we have to do. So I'm going to throw a 2 in front of that. A 2 makes all of this bigger. It's messy, of course, but nothing we can't fix. We then just go back through and fix up all the things we had here. So this is going to be, instead of times 2, I need to get to 4. So I'm going to times that by 4. Which means, of course, this one is multiplied by 4. So I get an 8 here. And, of course, we've got to fix up this 2 up here. Times by 4. Then we take out the red one. We double check that one. We needed to get a 12 now. Well, we've got a 6. Well, we know what we have to do. We're going to have to multiply both of those by twice as much, right? Because we're multiplying everything by twice as much. So we're going to be multiplying by 6. That gives this one a 6, and that gives this one a 12. And we put a 6 in front. Now, when I add up all the hydrogens, I get good old 14. Hey, that's a nice round number. Well, I have 2 here. Well, 7 times 2 makes 14. That's pretty convenient. So I just need to change this 3.5 to a 7. Hey, did you notice something? Did you notice the fact that basically every number that I had up here I've just multiplied by 2? Right? This used to be 3, but now it's 6. This used to be 2, now it's 4. This used to be 1, now it's 2. And this one used to be 3.5. If I take 3.5 and multiply it by 2, I get 7. There's the big trick. If you end up with a half number, you can actually save yourself a lot of work by just multiplying everything by 2. For those who caught on, for those who see what I'm saying, awesome. You've got a shortcut to work with. For those who are looking at that going, nope, I don't understand. That's fine. Don't worry about it. You can do it the way I just did it on the board. One step at a time, fill it out until you get it. And we got it, right? At this point, you might be remiss, you might be mistaken for thinking this must have just been a balancing chemical equations example. But no, that was just extra practice, because we can always use it. This is about combustion. Yeah, remember? We're talking about types of reactions. I know. So what are we looking at here? Well, combustion is about burning something. What we call hydrocarbons. And that always needs oxygen. And it always produces water and carbon dioxide. Now here's the thing. These 3 parts are always the same, right? I can't burn something without air. You know that. Oxygen specifically. And I always get carbon dioxide, and I always get water. The part that's going to be different is this part. Right now, I chose a particular chemical. I didn't need to. I could have chosen a different one. So the generic form of this is going to be something called CXHY plus O2 makes CO2 plus H2O. Oh, as an aside, you'll notice I wrote these in a different order. Order, that doesn't matter, so long as they're all on the correct side of the arrow, right? Both of these guys were products. Both of these guys are products. I just flipped around which one I put first. So this is combustion. You can burn any number of things with it, right? You can burn paper. You can burn propane. You can burn a candle. You can burn a shirt. Whatever. They're all made of a different mix of carbons and hydrogens, but they all done the same way: oxygen, carbon dioxide, and water. Okay. What you'll see here is that the next several pages have practice. Some of the practice will be balancing chemical equations, but not at first. At first it'll just be, can you identify what type of reaction it is? Right? When you see something, can you go, I know what that is? For example, get a little bit of board space. We'll just do 1 or 2 here. Let's say I give you, I don't know, this reaction. All right? It's even balanced for you. What is it? Synthesis, decomposition, single displacement, double displacement, or combustion? Let's look for key features. Do I see any carbon in there? No, so it's not combustion. Do I see anything dancing around, switching partners? No. I mean, there's only one thing on this side. Oh, only one thing. If there's only one thing on the product side, that means it must be synthesis. So this must be a synthesis reaction. Okay, that wasn't so bad. Let's try another one. Let's go with, let's go with this one here. KBr plus Cl2 goes to make KCl plus Br2. And we're not going to do any more balance practice at the moment because I just want to make sure we get to the other thing, so I'm just going to balance it for us. There we go. So what are we looking at? Well, okay, we've obviously got way more than just one product, so it's not synthesis. And we've got way more than one reactant, so it's not decomposition. Those are the ways we can identify those. It's not combustion because I don't see any carbon in here. Okay, so that's 3 of them off the list. Is it single displacement then, or is it double displacement? Well, this guy is kind of by himself, right? Like he doesn't have any other elements next to him. Yeah, there are two of them. That's because they're covalently sharing, as we hopefully remember. But he doesn't have anyone else to switch with. This, of course, is an example of a anion-anion switch, which results in somebody by themselves. And then this becomes single displacement. You could try to make the case for double displacement, but I'd prefer single in this case. You'll notice I just wrote it as a little shorthand. You know, chemists are lazy. We don't have to write more if we don't have to. All right, let's try another one. What do we got? What are the distinguishing features? That's what we're always looking for. No carbons, no switching of dance partners. What do we have? We have one reactant and two products. One reactant going to two products. This is going to be decomposition. Okay? Is this mostly making some sense? Maybe. Maybe. Let's do one more. I mean, I keep mentioning this one, but we don't have any examples of it, so we got to do one more. That one should be easy. Should be easy. There's carbon in it. There's oxygen in it. There's carbon dioxide in it. There's water in it. This is going to be combustion. All right. There are some examples. This isn't usually very challenging. I mean, once you've gotten this far, right, this is like you're learning how to put a period or a comma in a sentence at this point. You know how to put the words together. You know how to make those sentences. You know how to make sense of those sentences. You know how to make sure the grammar is right, the balancing. Now you're just making sure you can be like, oh, I know what type that is. Now, what we're going to see going forward is that being able to identify them gives us an advantage. But I'll save that for later. And see you guys next time.